Hello, my name is Patryk, and today we will try to address the latency spikes caused by discarding files. The lessons presented in this talk were learned while working on a real-world engineering problem at ScyllaDB. Briefly about me, I'm a software engineering enthusiast who contributed to various projects, and privately I maintain the HappyCat project. One may wonder what it is. So basically that's it. I tried to make him interested in computer programming, but he prefers to sleep. So before the actual problem is described, we firstly need to get a context to properly understand it. So let us start from a brief historical overview of differences between hard disk drives and solid-state drives. So as you probably know, hard disk drives store data using magnetic disks, and the access time depends on the location of the data on the drive. That's not the case for solid-state drives. They use flash memory, and the access time does not depend on the location on the drive. What is pretty important here is the fact that the low-level operations are considerably different, and for the purpose of this talk, we will focus on the override operation. Solid-state drives cannot overwrite data, unlike hard disk drives. In the case of solid-state drives, they need to firstly erase the data and then perform a write operation. This is called program erase cycle, and the reason for that is the fact that solid-state drives can and flash memory can program an individual bit from 1 to 0, but cannot program an individual bit from 0 to 1. And the flash memory is divided into blocks that are further divided into pages. Different operations use different granularity. Erase operation uses block granularity, and write operation uses page granularity. And as you can see on the slide, depending on the manufacturer, the typical size of block and page may differ. So page size is usually between 2 and 16 kilobytes, and the block size is usually between 256 kilobytes and 4 megabytes. Because of the way override works, it's faster to write to empty pages. So another important piece of context to properly understand the problem is the way removal of files from your machine works. So many file systems remove only the metadata related to a file when the file is deleted. So the actual data that was stored inside of a file is not touched and is not removed from the drive. So we may simplify and say that the file system forgets that something was written somewhere and starts treating that space as an empty space. However, later, when the file system tries to write to that space that it considers empty, the write operation might effectively become an override operation. So that can be a huge problem for solid-state drives, because we have already explained that writing to empty pages is significantly faster. So naturally, a question pops up. So could we somehow notify the drive that certain blocks are not needed and could be erased? And the short answer is yes, we can notify the drive. We could issue trim command that tells the drive that certain blocks could be erased during garbage collection process, and this way the likelihood of encountering the override operation is significantly lower. So that's of course good. So how to issue trim requests? Well, we have two standard means here. The first one is related to the fstream tool that is available on Linux. The user may explicitly call it or schedule a periodic job, and the fstream allows issuing trim requests for a given mount point or a certain range within the mount point, because it also supports offset and length parameters. Another available mean of issuing trim requests is related to the online discard mount option. So when we mount a file system, we may pass additional -o discard parameters that tells the operating system to issue trim requests in real time without interaction with the user right after the files are removed. So which method is better? Which method to choose? Well, as usually, it depends on the requirements for your system and for your workload. Basically, if some demanding workload is running in the system and it prevents an efficient usage of the FSStream tool, then the online discard mount option should be used. In all remaining cases, perhaps you want to use the FSStream tool. So now we are ready to get to know the actual problem. In ScyllaDB, we have seen cases where removal of huge number of SS tables caused latency spikes. The online discard mount option was a suspect. We thought that the removal of files propagate to the disk subsystems as a discard storm. Just to answer the question, why online discard at all? So without any form of discard, we have seen drives slowing down after a while, after which the usage of FSStream would restore them to health. However, if FSStream was run while some demanding workload was running, then bad latency would ensue. So the online discard mount option was an attempt to spread discard requests in time, just to, let's say, reduce the problem. So the suspect was online discard. Just to show how bad the spikes were, here is the chart obtained from the field, and we can see that the read latency increased from 5 milliseconds to 500 milliseconds, which is pretty bad. So now let us move to the part related to measurements and experiments. So the first idea for the fix was to implement simple rate limiting of number of removed files per second, and to verify that hypothesis, IO tester tool from C-Star project was used. This tool allows users to generate a defined pattern of IO operations to the drive. And just to underline, the obtained measurements that will be shown in next slides were obtained on AWS i3 2x large instance with Ubuntu 22.04. So here, to get a reference and to check the hypothesis, the results are presented for an experiment run in a file system for which online discard mount option was not run. The workload was issuing just 4,000 read operations per second, and each read tried to get 512 bytes. And on the left, you can see the number of removed files per second, because the workload was as well removing files. And we can see that when 128 megabyte files were removed, the latency spike did not occur in this particular setup. However, let us see the results of the same exact experiment, but run in the environment that had online discard mount option enabled for the XFS file system. And as we can see, the tail latency started to increase, and the more files we removed, the higher the spike was. In fact, what is interesting, during the experiments, it was concluded that it is not the worst case, and that the impact of unlinking a file depends on the file size and its fragmentation. So interestingly, on the next slide here, we can see results of similar experiment, but here we removed 4 times less data because the file size was equals 32 megabytes, but the files were much more fragmented. They consisted of 1 megabyte extents instead of 32 megabyte extents like in the previous case. And here the spikes were higher. So at this point, it more or less started to be clear that the problem is related to online discard mount option. So we wanted to somehow measure the impact of a single trim operation on a read and write operations. So in order to do that, Diskplorer tool was used. It is a set of scripts around a flexible IO tester that allows users to get read latency for different read IOPS and write bandwidth used for different combinations. And the idea was to extend that tool to run additional trim job that would trim the data written 10 seconds before with the same bandwidth that write job used, because well, the hypothesis was that the drive should be more or less capable of trimming with the same bandwidth that it uses to write, because when the drive is full, it needs to erase something to perform a write operation. So now we can see the chart from an ordinary workload run via the Explorer. This is for read versus write workload. On the left, you can see used read IOPS. On the bottom, you can see used write bandwidth. The more cyan the color is, the lower the latency. The more purple the color is, the higher the latency. So now let us compare this chart with a chart obtained for the workload that utilized this additional trim job. Well, so that's it. So for me, these two charts were pretty much the same thing. I even created a Excel spreadsheet to compare each cell of each chart to see the difference in latencies, but it also did not help. So I started to be confused, like why I did not see latency spikes. So one important thing to note is that the trim requests were issued evenly according to some period in this experiment. So I started to ask myself how XFS file system issues trim requests, and also why did I see latency spikes in the workloads run via the IO tester tool? And to get some answers, I decided to use BlockTrace tool, which is a tracing mechanism for IO for Linux, to inspect the requests sent to the drive. And it quickly turns out that XFS file system issues trim requests in a bulk, so at once. So even though rate limiting of number of removed files per second was implemented, the trim requests related to those removed files were issued by XFS file system at once per 30 seconds period. So after digging a bit, it turned out that the trim requests are issued when metadata related to removed files is flushed to the drive, and the flush period by default is equal to 30 seconds. And luckily, it is configurable, and the minimum value is equal to 1 second. So now let us see if increasing the frequency of issuing trim requests can somehow help us with latency spikes. So here you can see similar results, results of similar experiment, but this one used huge read IOPS. So the previous one used only 4,000 read IOPS per second, but this one uses 200,000 read IOPS per second. And still we are removing 128 megabyte files. And here we can see that the spikes were big. So let us see if changing the sync period and increasing the frequency of issuing trim requests can help. So it helped a bit when small number of files were removed per second, but in the case where a huge number of files was removed per second, it did not help. It even caused increase in P95. So, well, somehow, if we combine rate limiting of number of removed files and increasing frequency of issuing trims, we can, let's say, decrease the magnitude of latency spikes, but it does not seem to resolve the problem altogether. So just to summarize this part, the impact of removal of a single file depends on its size and its fragmentation, and rate limiting may not be able to help with removal of such files, because we can always have big and fragmented file, but we may use rate limiting and shorter sync period to decrease the magnitude of latency spikes. So what else could be done? Well, one important note is to know that unlink operation when the file is removed causes all extent of files to undergo trim operation at once. Like XFS issues trim requests for all extents of a file. So we do not have much control on the way the trim requests are issued. So maybe instead of removing the whole file, we could discard the file block by block, like in step-by-step way, and this way control the bandwidth of discarding file. And to verify that hypothesis, another experiment was conducted. It used fallocate function because it offers a flag that allows users to punch holes in files, and apparently when such hole is created and the metadata is flushed, XFS file system issues trim requests for that block. And here on this table, you can see that even when files with different sizes were removed via this block-by-block approach, here we discarded 512 megabytes per second in 16 32 megabytes blocks. The latency was more or less similar, so it seemed to be more stable than unlinking. However, this is not an ideal approach because if the removed file is highly fragmented and its extents are much smaller than the granularity of block used to discard data in this block-by-block approach, then still we can have problems. So here you can see that the highly fragmented file, when it was discarded in block-by-block approach, still caused problems, and the tail latency was much higher than in other cases. So let's summarize the talk. One important thing to note is that when we use online discard mount option and remove a huge number of files, then the latency of reads and writes may be badly impacted. We can see latency spikes. The impact of removal of a single file depends on its size and fragmentation. And basically, the more fragmented the file is, the worse the impact can be. XFS file system issues trim requests when online discard mount option is enabled according to metadata flush period. And by default, it is 30 seconds, but it can be configured to 1 second. Just by rate limiting the number of removed files per second and increasing the frequency of issuing trim requests, we cannot guarantee that the latency spikes will not occur. However, we may reduce the magnitude of spikes, so that's helpful. But still, another approach may be required. For instance, the approach that uses block-by-block discarding of a file. And we need to remember that if we implement such rate limiting or removal block by block according to a limited bandwidth, then the time needed to remove files increases, and the storage may be left lingering, but it is worth to keep stable latency. So the work on the fix is ongoing. Some experiments were done, some proof of concept code was also written, and the general approach to tackle the problem seems to be to implement the removal of files via block discarding, then estimate a cost of a single trim or some safety limit for discard bandwidth, and then ensure that this limit is not exceeded. Thank you very much.